Okay, so the next few videos are going to really center around what happens in the universe when objects are in really circular motion around central objects. Okay, so the first thing we're going to talk about is really Newton's law of universal gravitation. So one thing to note is that gravitation, right, is the weakest of the four basic forces found in nature, and in some ways really the least understood. We know where the other three come from. Gravitation is the one where it's like, where does it come from, what causes it? There's something called the gravity blip that they now have a sound recording that is representative of the gravity wave, and there's further research on that. So what happens is it is a force that does act at a distance, right? In fact, the range of the gravitational force is an infinite distance, okay? And without physical contact, and is expressed by the formula that is valid everywhere in the universe for masses and distance that vary from the tiny to the immense. And we'll get into the equation here shortly, all right? So the one that's credited, right, is Isaac Newton. I just wrote his last name because everybody just kind of just knows him as Newton, right? But Isaac Newton, if you want to be more formal, Sir Isaac Newton, was the first scientist to precisely define the gravitational force and then show that it could explain both falling bodies and astronomical motions. But really, he wasn't the first really to suspect that this same force caused both our weight here on our planet and the motion of planets, so our weight here on Earth and the motion of planets, right? And so Galileo, right, had contended that falling bodies and planetary motions had the same cause, right? And so he went up to the Leaning Tower of Pisa experiment, okay, where he just dropped objects and saw they did kind of fall at the same rate. Again, he's more doing, and funny enough, his last name is Galilei, right? So Galileo Galilei. In fact, I misspelled it. The first E should be an I. Okay, so it should be Galileo Galilei. Now, other scientists such as Robert Hooke, who we studied with Hooke's law, right, made some proposals. A gentleman named Christopher Wren, who did some research with Saturn, okay, the planet of Saturn, and Edward Halley of Halley's Comet fame, right, they also made progress toward understanding gravitation. But what it was that Isaac Newton was the first to propose an exact mathematical form, and to use that form, really, I think that should be formula, right? These words should be formula, not form, right? So he was the first to propose an exact mathematical formula, and to actually use that formula to show that the motion of the heavenly bodies, right, so these planets, should be conic sections. And if you remember anything from math, conic sections are hyperbolas, parabolas, ellipses, circles, all that. Okay, so Newton's law of universal gravitation. There's a little spot for a lot here. I should probably put a little bit more space, right? States that every particle in the universe attracts every other particle with a force along a line joining them. The force is directly proportional to the product of their masses and inversely proportional to the distance, or the square of the distance between them. And for that last fact, we call it an inverse square law, right? So because this here, talking about it, is inversely proportional to the square of the distance between them, we call this an inverse square law. And really what that means is that your force decreases greater, right, at a faster rate as you go out, as you get further away, right? So what does it mean? Your force gets a lot less as you go further away, okay? The equation is F, right, in capital G, subcapital G, and we're going to G m1 m2 over r squared, okay? In fact, I'll rewrite it over here to the left. All right, and so G is something called the universal gravitation constant. So universal gravitation constant. And it wasn't discovered by Isaac Newton. It was actually discovered by a gentleman named Henry Cavendish. Okay, it's now called the Cavendish Institute. He is the one who made the discovery of G. So Newton was able to kind of get the m1 m2 over r squared, that relationship, but Cavendish finished off the equation by actually determining what this constant was. Okay, and it has a value of 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Okay, now a lot of times you don't have to worry about the unit for this number because you're just going to plug in anyways the value. Okay, so the force is a force of attraction that acts over a large distance. Okay, where the weight, because these both are our force of gravities, right? So remember, the symbol we use for weight is F sub g, which literally means force of gravity. So one thing to note is that this universal gravitation force acts over a great distance, where the weight, right, the force of gravity, acts near the surface of a planet. Okay, but combining these two equations, you can use it to determine the g value, right, of any planet, or the acceleration due to gravity of any planet. And let's look at how that's done. So we would say F sub capital G equals F sub little g. So we say G m times the mass of the planet. So m, little m is the mass of like the object or a person, let's say, right? And we're going to compare that to the weight of the person at the surface, right? So the surface, the r would be the radius of the planet. Okay, for Earth it's 6.38 times 10 to the 6th or 7th meters. So do a little bit of algebra, okay, and you find that g equals big G, so little g, acceleration due to gravity, equals big G times the mass of the planet over the radius of the planet squared. I'm going to real quickly pull up the mass of Earth and all that, because we're going to use that, and I need to find the radius of the Earth too. And we're going to do that in meters, not miles. If you search in Google, it's automatically go to the miles. So it's 6.37 times 10 to the 6th meters. Okay, and we're going to, for this one, we're going to need the moon info too. So we're going to look up the mass of the moon, right, in kilograms. Don't look up the mass of the moon in the U.S. customary system. And we're also going to need the distance from Earth to the moon in meters, right? That one I actually looked up earlier. It's 384.4 million meters. That I kind of knew that one. So I don't sit here and think that I can just like do all this information in my head. Okay, so let's find the acceleration due to Earth's gravity at the distance of the moon, and then calculate the centripetal acceleration needed to keep the moon in its orbit, assuming the circular orbit is fixed about Earth, and then compare it with the value of acceleration due to gravity that we just found. Okay, so the first thing we're going to do is we're going to find the g value using this equation. So what we're going to do is we're going to find the g value at a distance of how far the moon is away from Earth. Okay, and so we're going to do 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the 24th kilograms. That one I actually did know. And we're going to divide that by 384.4 times 10 to the 6th meters, right? That's 384.4 million meters. And so this is going to give us the g value based on the equations that we just used to find at a distance of the moon, right? And so let's plug into our calculator. 6.67 e negative 11 times 5.97 e 24 divided by 384.4 e6, and that is not right because I forgot to square the denominator. And so I'm going to go up here, I'm going to fix that, put that in parentheses. Again, if you need to, make sure you're using parentheses in your calculator. Okay, and so that's a much better number. So 2.69 times 10 to the negative 3 meters per second squared. Okay, and so what we're going to do now is we're going to compare it to the moon, right? So the centripetal acceleration of the moon. So what we need to do is really find how fast is the moon moving, right? And so the way this is that the period of the moon, or the time it takes the moon to go around the earth, is 27.3 days, but we're going to need that in seconds. So there's 86,400 seconds in one day. Again, I was doing some work with these numbers before, so don't think that that I'm memorizing this. So it's going to be 2.36 times 10 to the 1, 2, 3, 4, 5, 6 seconds. So 2.36 million seconds. Okay, and the distance it travels is going to be, right, we're looking at one rotation, so it takes 27.3 days to go around the Earth, and so it's going to travel the circumference of that circle, right, so 2 pi r, so 2 pi times 384.4 times 10 to the 6th, so 2 pi times 384.4 e6, okay, and so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. 2.42 times 10 to the 9th meters. Okay, so that's how far it travels in that 27.3 days, which actually allows me to find the speed, right? Because speed is just distance over time. So it travels the circumference of the circle, right, in that time. So I'm going to do 2.42 times 10 to the 9th divided by 2.36 times 10 to the 6th. And so I'm going to do 2.42 exponent 9 divided by 2.36 exponent 6, and find that it's traveling at 1,025 meters per second. Okay, which then allows me to figure out, right, the centripetal acceleration. So v squared over r. So I do 1,025 squared over r, so 384.4 times 10 to the 6th. Right? And that's going to give me the centripetal acceleration. So 1,025 squared divided by 384.4 exponent 6, and I get a number of 2.73 times 10 to the negative 3 meters per second squared. So when I use Newton's law, I get 2.69 times 10 to the negative 3. And then when I use centripetal acceleration, I get 2.73 times 10 to the negative 3. If I divide those, 2.69 exponent negative 3 divided by 2.73 exponent negative 3, I get 0.985, right? When if I do 1 minus that number, it's going to give me kind of my percentage. So it's approximately a 1.4, 1.5% difference. So that's not much of a difference. And again, I circled right through my 1. Okay. So really the answers to this problem, right? So the G value at that location is 2.69 times 10 to the negative 3. My centripetal acceleration on the moon is 2.73 times 10 to the negative 3. And then my kind of my percent difference, or it's a 1.85% difference, right? So you can almost say that that value is really constant at that point. Okay, so that's how Newton plays into this. Next, we're going to do is we're going to look at satellite and Kepler's laws. So satellite motion, of which the moon is our natural satellite, right? But we also have satellites that orbit the Earth, just that are man-made satellites.